Okay. All right, so, right, the idea again is light changes speed as it passes from one thing into another, right? The index of refraction is an indicator of how much slower the object's going to be. It's also an indication of how much the light's going to bend as a result, right? The greater the index of refraction, the bigger the change in speed, the more the light bends as it goes from one substance into another, one medium into another. Okay. Next slide. So this is just a list of, give you an idea of some different materials for in the index of refractions, right? So vacuum is 1, right? Because the speed of light over the speed of light is 1, right? Air you can see is 1.0003, so effectively very minimal change in velocity when it goes from light into the air, right? Into our atmosphere. That's the sunlight passing out of outer space and into our atmosphere as it passes when we're looking at the light, when we're looking at the sun, or we're looking at the moon, or at the stars, so on. All right. And you can see, right, the index of refraction increasing over with different materials. So the greater the index of refraction, the slower the light is that passes as it goes through that substance, and the greater light bends. That's why diamonds are so shiny, because there's big changes, and with all of the cuts and the different cuts on a diamond, you get that's where you get all the sparkly diamonds if it's nice and clean, because there's so many bends and changes and reflections and refractions in a diamond. Okay. You don't have to have this written down. Anytime you ever need a value of index or refraction, it will be given to you. Okay. So let's take a look at this. Hopefully, are you seeing are you still on the slides, or did?
Yeah, we're still on the slides.
Okay, so let me stop sharing for a moment and share the simulation now. Share the physics simulation. Here we go. Okay. Now I'm assuming you're seeing the simulation. Did I get this right? All right, there should be a, can we see this?
Yep.
Yes, I can see it.
Okay, so here's the idea, right? This is a laser beam. This is a laser that's going to shoot a laser beam. And there's one substance on top. In this case, it's air. So we're shooting the laser beam out of the air or through the air, and then it's going to hit the water, right? Water here on the bottom. And when it enters the water, it bends. So for example, here, right? I don't know what happened to our lit. Uh-oh, what happened? Reset, go. I was just using this morning and it was working. Clear. Air on top, water on the bottom, go. Ah, there we go. All right, so when you see this, you're seeing the laser, right? The laser comes, it hits the water. Some of the light gets reflected, so the angle of incidence and angle of reflection are equal. And some of it passes into the water, and you can see that it bends. So show the protractor. There it is. When I move my protractor onto that spot right here, right, my angle of incidence, the angle of incidence is here is 66 degrees. The angle of reflection is also 66 degrees, but the angle of refraction now is 40, what's that say, 42 degrees? Right, so the light, as the light leaves the air and enters the water, it bends. Notice what happens in terms of speed. The air is index refraction 1.0003, water index refraction 1.33. So does that mean the light speeds up or slows down as it goes into the water? The index refraction is greater. Is the velocity faster or slower? Do you remember? We just talked about it. I went through it quickly though. Anyone remember? Slower. Yeah, somebody answered me. It's slower, right? The greater the index of refraction, the slower the air passes or the light passes through that substance. Right, so, and we can just repeat it. You know, I can move the reset. I didn't want to reset. I should have hit clear. Show my protractor again. When I move the laser, why did that happen? Go. Why am I having issues with, there we go. Right, this was the original setting. We just did that one. The same thing happens. God damn it. Go. Beautiful. All right, that was the original one we already looked at. Let's move this here. Go. I don't know what's going on with my simulation. Try again. There we go. All right. So again, angle of incidence and angle of refraction, both, if I move my protractor on the right, we can get it zeroed up. Both 49 degrees, but my angle of incidence or angle of refraction rather, incidence, reflection are the same. Refraction, the angle is smaller. All right, so notice the pattern here is as it slows down, the light bends towards the normal. All right, as it slows down, the light bends towards the normal. And as you can imagine, if I put my laser underwater, the opposite should happen. So as the light speeds up, it should bend away from the normal. Uh-oh, it didn't refract at all, didn't go through. Let's start over here. It's called total internal reflection. That didn't work. Why is this never working? Why is my life so miserable? Come on, that's straight, that's not right. Clear, reset, let's start at the beginning. Bring it down here, show my protractor, go. Total internal reflection. We're going to talk about that later, but you can see it. This is called total internal reflection, where none of the light passes through and refracts. We're going to talk about why that happens sometimes at the end of the set of notes today, if I can get this thing to work. We might talk about it sooner than I want it to. Go. Damn it. Let's try again. Clear. Go. There we go. Okay. All right, so again, notice this time it's speeding up. Right, so the angle of incidence is 20 whatever degrees that is, 25 degrees. But as it speeds up, it goes from a slow stuff, water, into fast stuff, air. The angle of refraction bends away from the normal, and now it's up to 35 degrees. Okay? So we can do this for all of these things. Clear, we can have different settings here. That's not what I wanted to do. Let's make the bottom. Let's look at it here, right? Do it this time. Go, work, 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 work. Yeah, nice. Show protractor, right? Angle of refraction is 42 degrees. If I change the substance, we change the substance to oil, a larger index of refraction, it should have a greater change of in direction. So my angle of refraction should get smaller, right? The slower it goes, the more it's going to bend. So it was 42 through water. Oil, the index of refraction is a little greater. It's now 37 degrees. If I make the bottom thing a diamond, right? The index of refraction is 2.4, so it's much slower. So we should have a much greater bend. And you can see we do. Now we're all the way down a 20-degree bend. Okay. Any questions on this idea of refraction and index of refraction and how it affects how much there's going to be a bend? Okay, so let's go back and finish up our notes here. Okay, right, so this is the idea, right? And we're going to talk, Snell's law is the next slide here. Oh, it's 2 slides away, right? This is what we just talked about, angle of incidence, angle of refraction, right, and the bending. Okay. And some of the, you can see some light gets reflected and some passes through and refracts. Here this time, right, slowing down, bends towards the normal, speeding up, bends away from the normal. Okay, here's Snell's law. All right, Snell's law, this formula is on your worksheet or on your formula sheet, right? It mathematically explains everything we just did, right? The angle of refraction depends on the speed of light of the two materials and the angle of incidence. So N1 is the index of refraction of substance 1, sine of theta 1, right? Obviously, then that's the angle the object is going through, or the light is passing through when it goes through substance 1. It's equal to N2 sine theta 2. Right, again, index of refraction of substance 2, angle passing through substance 2. All right, so here's in this little picture, right? The angle of incidence is 60 degrees as it passes through air. It slows down as it passes through the glass, so it bends towards the normal. There's my angle of incidence. As it's leaving the glass and going into air, that same angle becomes the angle of incidence on the other edge of the glass, and the angle of refraction as it passes back through air. So the image appears to be, right? So if you can imagine, this is a big enough, thick enough piece of glass, somebody is out here looking at some object, to this person out here, the object appears closer to the glass than the object actually is because of this bending of light. Right? We all been to the aquarium? I assume at some point in our lives we've all been to an aquarium, or you've looked into water, even if it's just a fishbowl. the fish actually, when you look into the fishbowl and you see the fishbowl and you look from at an angle through the glass, you think you know where the fish is, and if you look from above, the fish isn't actually in that location because of this stuff, refraction of glass. You think you're looking at the fish, and you think the fish is in this location, appears to be in this location, but in reality, the fish is in that location. And it's even more severe because there's the change through the glass and then another change through water. It's not air, glass, air. It's right. It's air, glass, or water, glass, air to your eyes. Right. So even bigger amounts of changes. Okay. Moving on. Last slide here for today then becomes this idea of total internal reflection. Right? If the angle of incidence is big enough, then right, the sine of the angle of refraction is greater than or equal to 1. Right, because here we go, right? This is the idea. Water into air. So as water passes into air, it speeds up and the angle of refraction bends away from the normal. So it goes here and then it bends away from the normal. And then there's a reflection, right? Some of the light is reflected, some of the light refracts. We increase the size of the angle of incidence. Some of the light reflects, some of the light refracts. We increase the size of the angle of incidence enough, it's going to bend away from the normal so far that it's actually 90 degrees. So none of the light actually escapes the water. That's called total internal reflection. None of the light escapes the water. And if we make the angle of incidence even greater, not only does it bend to 90 degrees, it doesn't even, it's more than that, and then it reflects back. Okay? So it's called total internal reflection. When the ratio, right, because this would be N1 sine theta 1 is equal to N2 sine theta 2. Well, if sine theta 2 is 90 degrees, right, the sine of 90 degrees is 1. Is that correct? That's sine of 90, yes. The sine of 90 degrees is 1. So then this ratio, when this ratio of N2 over N1 is equal to or greater than the sine of the angle of incidence, you get internal reflection. Right? That's how fiber optics work. Right? One more slide. Right? That's how fiber optics work. That's the idea. So we send the light here, it passes, and it never leaves the tube of glass, and the light passes through. Okay, and that's how fiber optics work. I have a demonstration of that. I don't know if I'll be able to show it to you. All right, any questions? Any questions? That's all the material, right, on refraction and Snell's law. Right, we would do a lab on it, but obviously we can't because you guys are here or aren't here, and there's no way the lab, you have to be able to just no way to set the camera up so you can see. This thing is this piece of plexiglass tube, right, shows total internal reflection. And I'm not sure if I can show this, if you can see this or not. We'll try. right? I take a laser beam, and if I put the laser beam into this end, you can see the light come out the other end, right? You can kind of see it's kind of a purplish shade. I wonder if I turn the lights down lower. If you can see it better. Hold on, I'm going to turn the lights down. All right, here's my purple laser beam. So where's the camera? There it is, right? So you can really see this total internal reflection, right? The laser beam, I don't know here, you can see, can you see where's the camera? There it is, right? You can see the beam reflecting through the piece of, excuse me, reflecting through the piece, but never refracting through, and never leaves the tube, right? It passes along, and then you can see at the end, the light finally leaving the tube. All right, that's called total internal reflection, right? Because the ratio of the light to, or index refraction of this piece of plastic to the ratio to the index refraction of air, right? If I have my angle great enough, or I'm sorry, right? The angle of incidence is small enough, I get some reflection, which you can see, but what you can't see is there is also, because my angle is small enough, there is some refraction, and there's a spot on the wall over there where the light is. But if I bend it and make my light go in at a great enough angle, that spot disappears. That refraction spot disappears. Where, let's see if I can find it. Where was it? I just saw it before. Now I'm losing it. There it is. Okay, right? Not really, can't have a small index or small angle of incidence, and I can get a little bit of a, over there, an angle, a spot on the wall where you can see the refraction also from the laser. Okay. Anyone have anything you want me to go back over at all on any of that stuff? Go back to any of the slides, go back to the simulation or anything? No? Okay, so I am going to stop the recording.